Very good morning to everybody. Welcome to session 2. In this session, we will learn about constraints and degrees of freedom. Let's recap what we have learned in the previous class. We learned classical mechanics. The mechanics based on Newton's laws of motion and alternatively developed by Lagrangian, Hamilton and others is called classical mechanics. If the external force on the system is zero, then its total linear momentum is a constant of motion. In absence of external torque, the total angular momentum of a system of particles is conserved. Constraints. The limitations on the motion of a system are called constraints, and the motion is said to be a constraint motion. They are classified into holonomic and non-holonomic. The learning objective of this session is to understand time-dependent and time-independent constraints, the degrees of freedom, and configuration space. By the end of this session, you will understand the constraint motion and their types, the degrees of freedom, and configuration space. In the previous session, we learned the constraint and their types, namely holonomic and non-holonomic. They are further classified into scleronomic and rheonomic constraints. If the equation of a constraint motion is dependent on time, they are known as rheonomic constraint. Example, a pendulum with a varying length. To bead on a uniformly rotating wire. Number 3, deformable bodies. Number 4, gas expansion or contraction filled in container. If the equation of constraint motion doesn't contain time explicitly, they are known as scleronomic constraints. Example, a rigid body, a pendulum with a fixed support, a gas-filled hollow spheres. In this slide, we observe a pendulum with a variable length is an example of rheonomic constraint. A deformable body and a bead on a rotating wire, gas expansion. They are all the example of rheonomic constraint. Whereas a rigid body and a pendulum with a fixed support, gas-filled hollow spheres, they are the examples of scleronomic constraints. A body in a state of rest or motion is described by a variables. Example, a body moving in a straight line is described by either x, y, or z coordinates. If a particle moves in a plane, we need two coordinates namely x and y, or yz, or zx. Likewise, if a particle moves in a three-dimension, we need three coordinates, namely x, y, and z. These minimum number of independent variables are coordinates required to specify the position of a dynamical system consisting of one or more particles is called as the number of degrees of freedom. For a particle moving in a free space, we need 3 degrees of freedom. For two particles moving in a free space, we need 6 degrees of freedom. So, for a particle, 3 particles in a free space, we need 9 degrees of freedom. Likewise, if a system consists of n particles moving freely in space, we need 3 n independent coordinates to describe its position. Hence, the degree of freedom is 3n. However, if the particles or motion are restricted within a constraint, the number of degrees of freedom reduces by the number of constraints. So to understand, let us consider a monoatomic gas, which is like a free particle in space, so it needs totally 3 degrees of freedom. Examples: helium, neon, argon. For a diatomic molecules, which is like 2 particles in a system, we need totally 6 degrees of freedom. However, if the distance between the 2 particles are fixed, then the number of constraint is 1. So the degrees of freedom reduces from 6 to 5. Example: hydrogen and oxygen. For a triatomic non-linear molecules, the number of molecules are 3. The degrees of freedom is 9. However, if the distance between the 3 particles are fixed, then the number of constraints are 3. Then the degrees of freedom reduces from 9 to 6. Example: water. For a triatomic linear molecules, the degrees of freedom is 9. However, if there are 2 constraints, then the degrees of freedom reduces from 9 to 7. From this, we understand that the number of degrees of freedom decreases with the number of constraints present in the system. So, if a particles involving k number of constraints, then the degrees of freedom for such particles is found to be 3n minus k, where n represents the number of particles and k the number of constraints. So thus we define the degrees of freedom is defined as the minimum number of independent variables or coordinates required to specify the system compatibly with constraints. A configuration space. The configuration of a system of n particles moving freely in a space may be represented by the position of a single point in 3n dimensional space is known as configuration space of a system. So in this session, we learned about the time dependent constraints known as rheonomic constraint and time independent constraints known as scleronomic constraint. A degrees of freedom is defined as minimum number of independent variables or coordinates that are required to specify the system which are compatible with constraints. The configuration of a system of n particles moving in a space may be represented by the position of a single point in 3n dimensional space. Is called as configuration of a system. Now we shall have a small MCQs session of this. Question number 1. Which constraints equation of motion are independent of time? Option A, holonomic. Option B, non-holonomic. C, scleronomic. And rheonomic. The answer is scleronomic. Question 2. Which constraint equation of motion are time dependent? Answer is rheonomic. Question number 3. The constraint on a bead on a uniformly rotating wire in a force-free space is an example for rheonomic constraint. Question number 4. The degrees of freedom for a free particle in space are. Answer is 3. Question number 5. The degrees of freedom for n particles in space are. Answer is 3 and. Question number 6. The number of degrees of freedom of a system of n particles subjected to k constraint is. The answer is 3n minus k. Question number 7. The degree of freedom for a linear triatomic molecule is. Answer is 7. So you can refer the sources: Classical Mechanics by Goldstein, Classical Mechanics by Gupta, Kumar and Sharma, Classical Mechanics by Takwala and Puranik, Classical Mechanics by J.C. Upadhyay. Thank you. Hope you enjoyed this session.